Now, we have learned that frame relay consists of many circuits. So we can deploy many circuits to connect all our office sites together to provide a full mesh connectivity. So in simple English, the circuits from frame relay provides circuit connections to every destination. Every destination has a connection to every destination. So we call this a full mesh connection. Now, a full mesh connection is very reliable. It's very reliable because there's a lot of redundancy built in. If this link breaks, the other one can take over. But full mesh connection is very expensive to set up because you need to take into you need to buy a lot of redundant links. So in the real world, we tend to do the other extreme method, what we call the hub and spoke deployment, whereby all the remote sites converge onto a hub and from there travels through the hub to reach the various remote site. So everything must every remote site must go through the hub to reach the other site. So this is not that reliable because you could have a single point of failure, right? Because you could have a single point of failure. But it is not expensive to deploy. So that's why in the real world we tend to use a hub and spoke topology when deploying our frame relay connection services. Now, of course, over the years people learn to compromise in that not every location needs to be fully meshed and not every location can do hub and spoke. So partial mesh is like a compromise solution. Some VIP locations would require to have a fully meshed connection, while others not so VIP location will have hub and spoke connectivity. Now, as we have mentioned, hub and spoke is the most common deployment solution when setting up a frame relay topology. Now, but one thing to remember that a hub and spoke topology sometimes can create routing issues. Now, in this example, in the beginning, all the circuits report to the same interface S0. So in the beginning, all the circuits are reporting in to the same interface called S0. So what happens is you have a problem of a split horizon. Routes that come in on one interface cannot go out the same physical interface. But wait, I'm going out through a different circuit. Unfortunately, we don't care about which circuit you come in from. We care about which interface you came in from. So if you came in from S0 interface, you can't advertise out of S0 interface to avoid routing loop issues. So one of the way to overcome this routing loop issue, because all the circuits report to the same main interface S0, is to break all the main interface into a lot of sub-interfaces. So each sub-interface takes care of one DLCI circuit, one DLCI circuit, one DLCI circuit. So each sub-interface takes care of each circuit connection. Now, because of that deployment, the circuits are no longer coming in on the same interface. They are coming in on different logical interface. So you come in on one logical interface, you are able to go out to a different logical interface. Okay? So this is how to prevent routing loops in a hub and spoke deployment. Okay? We break the interfaces into a lot of sub interfaces so that the routes can be going through different logical connection, advertised through different logical connection. Now to configure a simple frame relay static map. So what is the static map? Is to map the IP address, the next hop IP address to be specific, with the local DLCI number, local circuit number to reach this next hop IP address. So as I've mentioned, you can either do manual configuration like this, or you can do dynamic discovery through the use of inverse arc. But in this example, this is how you set up a manual static frame relay map to map the local circuit with the next hop IP address in this example.